Okay, so continue it with the analytical method. अब हम देखेंगे कि uh, how we will do the modeling or the overall analytical path. So the first step is about modeling. Now in engineering systems, the physical models and their physical systems and their models are distinctly discussed from very basics to the advanced. I just showed you कि किस तरह एक register जो है, it may be a very simple constant V equals to IR model, where R is constant. And we can also make another model of V equals to I, where R can be a function of the temperature, okay? And the examples are, for example, here, the resistor with the constant resistance is a model, but it will burn out. It is, of course, because of the high temperature and current if applied voltage is over a limit. So this power limitation is often disregarded in its actual analytical study. So usually we take V equals to IR model and avoid this power limitation. And this because of this thing, it becomes the job of the instrument engineers and designers who are actually, or the commissioning engineers, or anyone else who is basically responsible to select for example, the resistors. So their specifications through the data sheets according to the environment in which they will be installed, and the current will go through them. Okay, so the designer has its own role on focusing on the analysis and signals, and the real implementation, realization. So this part is a creation part, and the real realization part, like the implementation or selecting and buying the resistor, the instrument engineers normally, they are mainly responsible to select according to the specification and the requirements. Okay, and here comes the standard or procedures to follow. For example, in oil and gas industry, the API standard guides, and in others there might be IEC standards for selecting the appropriate resistors. Now coming back, so that the power limitations are not disregarded. Okay, so this is important. The second can be an inductor with a constant inductance, is also taken as a model, but in reality, this L is will vary, and L is a function of the current. Okay, so it may vary with and the inductance will vary with the current. And so the modeling is very important problem. It itself is a big area, and this is very important for the success of the design, and that we model it properly. And for every model, there is a limit. Okay, so when we are applying, we have to have we must know that the model is still valid. Okay, when we are focusing on some operation. Okay, for example, for a generator, if we have a model of a generator, and that is designed to apply from let's say generator for 25% to let's say 75% is applicable. So it may not be valid. Okay, generator model may be valid for this, but may not be valid for above 75%. Okay, for the generation. Okay, so in that, maybe we will think about the model number 2, or we should not use the model 1 for that purpose. Okay, continue with the modeling. Note that a physical system may have different models. Okay, this is what we are talking about. In case of a nonlinear system, we may have multiple models. Multi-model approach is also used, for example, in helicopters. It depends upon the questions actually we are trying to solve or being asked. So for example, an electronic amplifier is modeled differently at high and low frequency. So if you are making a low frequency circuit amplifier, it will be taking different model behavior. For high, it will be different. And a spaceship can be modeled as a particle when we are discussing its trajectory path, and as a particle, okay? But it may be taken as a rigid body when we are talking about maneuvering, or as a flexible body when we connect it to the space station. So the spaceship can be modeled from three different perspectives. Okay, different perspectives. Right. So what we need, so what is needed to develop a suitable model for our physical system? This is a very important question. We actually need to understand thoroughly the physical system. This is the first thing, how the system works. This is first learning. And then we also have to understand its operation range. So the first thing is understanding how the physics behind the system, general physics and maths and the chemistry. And then we focus on its operation range, what exactly the range we are trying to use it, okay? Um, so here is a note again that we will use the term system to refer to a model as well, okay, for the physical system. Okay, so system means we are referring to the mathematical model of the system that we are talking about. Uh, Modeling to the mathematical description. So we are done with the modeling, and now we are moving to develop some equations. So this is how we are highlighting here as a mathematical descriptions. Now, a physical system is a device or a collection of devices which actually exist in the real world. And so the physical system is a bigger term, and a system means a small model of the physical system. Okay, so physical system means we are trying to highlight that we are talking about all the whole process, which is a collection of all the devices. But when we talk about, when we say system of a physical world, it means we are referring to the model that we are studying. So once a system or the model is selected for a physical system, which is a subset of a physical system, may have different models or different systems, right? So when we select, the next step is to apply the various physical laws to develop the mathematical equation. Now the target is, this is our target, to develop the mathematical equation, okay? So these mathematical equations now will help us to describe the system. For example, again, the same example, Kirchhoff's voltage and current laws are used to develop the mathematical equations for an electrical circuit. Newton's laws are applied to the mechanical systems, shaft and others. And the electromechanical systems will use both of them. Integration of, for example, a shaft connected with a prime mover. Okay, if we talk about some kind of a generation. So in generation, we may have a hydro plant, okay? And that hydro plant, there might be a prime mover that is connected to a shaft. This shaft may be connected to a rotor of a synchronous machine. And this is the mechanical torque. And then the rotor will be rotating around a stator. Okay, and this stator will have induced magnetic field. So this is the way here we will have The stator will start having the electromagnetic here. The electromagnet will balance this torque. So we will have a torque from electrical side. We will have a torque from mechanical side. Okay. So this is electromechanical, and we have electromagnetic side, and the both will balance each other, and we will have a synchronous speed running for the motor. So this is what I'm talking about. The electromechanical, for example, system will be integration of the electrical and mechanical laws, for example, electrical laws and the mechanical laws and the electromagnetic laws. Okay, right. So continuing from here, um, so when it comes to the equations, there can be different type of equations that will make the model of a physical system. And we may have simple linear equations. We may have some nonlinear equations, integral difference equations, differential equations, and some other equations as per the field that we are working for. So depending on the problem under study, one form of equation may be preferred to another form in describing the same system. This is a big task, having a good mathematical description. This is key. So a system may have different mathematical equation descriptions, just as a physical system may have different models. Okay, so this is nice. Mathematical descriptions. After having the equations, we are ready to make some analysis, putting different values of the parameters and plotting them on the computer simulation. MATLAB will help us to do the dynamic analysis. We will do some demos of complete systems and see how different inputs against different inputs, how it works against different disturbances, it works. So after mathematical description is obtained, this is the very important thing. This part is done. We can carry out the analysis, and we can do both of them. We can do the quantitative analysis. We can do the qualitative analysis. Qualitative analysis is basically about like region based analysis. Okay, so we may talk about like during for this range it will be stable, and for this range it may not be stable. Okay, so at this moment I would like to mention, for example, if there is something like s minus s plus 2. Okay, s plus 2 is something, and so this means s equals to this will be unstable when s is equals to minus 2, because at s equals to minus 2 we will have 1 upon minus 2 plus 2 becomes 1 upon 0. So this becomes like a pole infinity. Okay, and in quantitative analysis, we are interested in the responses of systems excited by certain inputs. Certain inputs may be the step, a sign, impulse, okay, and others. And we are interested in the general properties of the systems, like, okay, for example, a step of 1, 2, 10, okay, percentage, how much step is will keep my system stable or not, or what will be the controllability, what will be the observability. Okay, so these are the things. In qualitative analysis, actually they help us to lead to design techniques. Okay, so what will be the value of let's say k, for example, let me expand this thing, the same thing. So if I have 1 upon s plus k minus 2, and then I will ask, okay, what will be the what values of k will result in a stable system. So you might come up with some values a range of values. For that one, we will find some range of values for K for system to be stable. Okay. So we will, so design techniques, they help us. Linear matrix inequality is another example of that. Okay, so now, so there are two classes of model-based strategies. First is called open loop control strategy. It may have the controller will determine the inputs without looking at the output. Okay. And we already have the physical objects, plant, process system. It is defined here. We have the output, but controller has no idea. So it is already, it sometimes it is time based. Okay, time based. So you put the water in it. If it may be a washing machine or a dishwasher. So you put the water, okay, up to the level, and then you turn on the timer, okay, for 10 seconds to do this, for example, rinse. Okay, your water intake is automatic, and then for after doing this for 5 minutes, okay, you may spin, and then spin right. Okay, then for 5 minutes you spin left. Okay, and then you for 2 seconds or for 10 seconds you rinse. Okay, and so on. So but we have no idea about the output. Okay, so this may be a time based. This is open loop control. The second is the closed loop control. In closed loop control, we actually close this. So the loop is closed here, and the controller has a sense of the output by its measurement. So the controller uses the plant output to help determine the plant input, so that this input is determined based on the current situation. The advantages, it becomes like robust to external or internal disturbances. For example, for any reason, if the water intake is not enough, it will take proper action. It will stop the valve and other things. And also for the internal disturbance, maybe it is sending a signal that spin right and the motor is not moving at all. Okay, if there is some signal that if this spinning is being done, then it will know. If spinning is not being done and we have a feedback signal, controller is trying to ask the washer that, okay, you have to spin, and the machine is not spinning, controller knows it, so it can stop. So internal as well as external disturbances, the controller will take proper action and avoid any wastage or excessive control actions. Examples are like air conditioners are the feedback closed loop control, refrigerators are feedback control, closed loop control, and rice cookers, for example, they are also automatic ones are closed loop control. And light switches, for example, you turn on the light and the light doesn't glow. So what will happen? The switch will not be closed. It is still trying to send the current, and the same goes for the ovens as well. Now comes the analysis part. Analysis of a system enables us to see if the response of the system is satisfactory or not. Analysis is very important. Okay, every step is important and at its spot. So it will enable us how the response is going and if it is satisfactory or not. And in case the response is unsatisfactory, the system must be modified or replaced. And analysis is important. So analysis enables us to study the response of the system against the parameter variation. We can study against the parameter variations, and even we can figure out the parameter ranges where the system performs satisfactory. So for example, in case of V equals to I R T, temperature dependent. So here we can make an analysis and we can figure out the temperature ranges T minimum to T maximum, for which the voltage will be in the proper range. Okay, so corresponding to that, V out will be from minimum to the V maximum, and then we figure out, okay, this is the range that you should use your the resistor is will behave properly from, let's say, 0 degrees centigrade to, let's say, um, 45 degrees centigrade, and beyond that, if it increases beyond 45 degrees, your voltage may be in a different range. So this is the parameter variation. We can, if I have this equation here, I can put the parameter values and calculate the analysis. So analysis also helps us to identify the required specification for a controller or compensator. This is another aspect. So we study the parameter variation. This is one. We study the required specification of the controller, and the basically the analysis heavily depends on the model. So if the model is good and detailed, appropriately detailed, so I should say the model should be detailed. Okay, so the as per the required specifications and the quality. Okay, so this is an important thing. Then we are able to make some products as per the requirements. So it should be carefully developed. So if the model is poor, then the performance analysis will have no good value. Okay, so we have to have some good data. Analysis is all about very good, having a very good data, and having a very good data requires a very good mathematical model. So analysis is not useful if our model was not appropriate. Therefore, selecting a model that is close enough to a physical system and yet enough simple enough to be studied analytically is the most difficult and challenging problem here in the system design. So we have to keep a balance. We have to keep it model detailed enough as well as the simple. Okay, so this is a real challenge. And once we have a good model that is simple as well as showing or including all the required details, we are done. So what is needed to develop a model? So developing models for physical systems, they require, number one, we also call it domain knowledge. So the domain knowledge or the knowledge of the particular field is very important. Even, for example, in data science or anything, we talk about it, but ignoring this thing, the experts of the field, if we don't talk to them and try to make the models without their expert advice, we are on the wrong track. And the second thing is we should have some very good measurement devices so that we also collect the proper data. Okay. And having these two things, the third thing will come here, which actually we talk about is the technique or the methods. For example, methods of, let's say, for example, the linear control theory that this course is all about. Okay, then the methods come here. Some examples are to develop the models for, let's say, transistors. Someone we don't develop them, but someone who has done the transistor models, they have the knowledge about the quantum physics and they have the laboratory setup, so that they tell us, okay, the SCRs and other transistors, how they are actually working, and we get the data sheets and the graphs and the equations, okay, that we use. So researchers have done it, and we have useful models for the transistor. The only thing is we have to understand, we have to go read all the data sheets and understand and apply these things. Then to develop a model, for example, for the automobile suspension systems, we need the actual testing. Here comes the data and the measurements. And we cannot just sit and make the paper and pencil diagrams. Okay, so both things go hand in hand. And the computer simulations, they help us, they help but cannot replace the actual measurements. So we do all the things: empirical, mathematical model, and experimental data, computer simulations. So we will cover a little bit. This is not the objective of this course to develop models, but we will partially cover it so that we know how to deal with it when it comes to on table. And then mostly we will assume the model is available for during this course. Okay. So now let's go through some models available for the linear systems. Uh, from theory and control perspective, a linear system is simply described by an integration, okay, from T naught to T, and there we have a sort of a function. Okay, this is the system representing the system, and we have input here. Okay, so if you apply an input, some kind of input is applied over the time. Okay, and this is u of t, and we apply it. So the rest will be based on multiplication of u of t, okay, with respect to the input. Okay, this may be its y of t. So y of t will heavily depend upon the what you have applied here, u of t, y of t, and what is the function here, g. And if you see, it is the function g is a function of t and tau, right? We will study the difference between these two. So this equation describes the relationship between an input and an output, u and y. And this is called the input-output or external description. And the mathematical equation that describes or makes this relationship is the system G. Luckily, if we have the lump system, lump means you have the similar one that I draw, you can actually represent with a finite. If the system can be represented by, let's say, a finite uh, uh, internal components, let's say C1, we have V1, we have V2 here, or V out, V in, and V out. So if we have like two resistors, one capacitors, a finite number of internal finite components, then we can say, okay, what will be the voltage here? What will be the current through this one? What will be the voltage across this? So this is called a sort of a lump system. So then in that case, we can describe it by these two equations where x dot equals to ATX plus BUT and y equals to CX plus TU. This is a time, this is called the internal description model. And by this we have, okay, so this is also called the state space model. Okay. And what's happening here is we have the input here. We have the output here. And then we have something called X. What is now X and X dot? This is basically the set of states. And this is the internal element that we are talking about. So internal voltage, for example, what is the internal voltage V1 here? Will go to X, and the current I1, for example, will be the so V1 and I1 can be the part of this X. Okay, so internal description will take all the states, internal states of the system. Of course, one state will be reflected as the output here. So the vector X is called the state, and the set of these two equations is called state space, or simply the state equation. Okay. So this is a little description about the input-output model. and also the state space model. Okay, right. So keep in mind we will continue. So this course basically focus here, and what we are doing focusing is on the on most of the part we will focus on the state space. So now sometimes we have the linear system, but the linear system is time invariant. Now this is the difference between the previous and here. In the last slide, we said the G is a function of the time and also tau. So it heavily depends upon the time, as well as when the signal I mean the input was applied. Okay, so for example, think about it. If tau is equals to 1 second, okay, you applied on the time window, you applied a step here 5 volts from 0 to 5 volts at let's say 1 second, and then you apply the step at, let's say, or the same step at the 3 seconds, and then the 5 seconds. So in every case, your output will be different. It depends upon the system will behave differently for different applied, same signal applied at different times. So that's why we use a comma. So it is an independent one. But in case of time invariance means it doesn't matter. It does not matter when you apply the input signal. Okay, so the system will behave the same. So in that case, there is only t minus tau will be the time instant when we actually it will only be shifted. This means the same response of system but shifted. Okay. So if a linear system has an additional feature, this is a relaxed or more easy feature, that this is also time invariance. Like time invariance means it doesn't matter that when you are applying, it will behave the same way, except that it will only shift. So then the previously equations like 1.1, 1.2, 1.3, they will become y of t will become, this is the only change in this equation, 1.1. And there is a little change from here. Previously, this was x dot of t equals to a t x of t plus b t u of t. So now bt will become simple b and the a of t will become simple a. So it means they also become time invariant. In the previous case, you have a of t, b of t, c of t, d of t. But now we have time invariant ABCD constant matrices. Now in this class of systems, time invariant, we have very good tool, and we learned it well before in many courses, Laplace transform. Now the Laplace transform will make our life very easy. Okay, so it will help us in the analysis and the design of the controllers as well. Okay, so what Laplace basically is going to do? What Laplace is going to do is, if this is a system and we apply the Laplace, it will directly give us the transfer function form. So where this circumflex, this hat, small hat here, circumflex, is denoting the Laplace transform of the same variable. So if this is a time domain variable, we have the S domain, Laplace domain variable as with this circumflex. So this G is called the transfer matrix, and note that both 1.4 and 1.7 are the input, output, or external descriptions. And the former means the previous one is the time domain, And the letter one, letter means this one is the frequency domain, okay? Right? So keep in mind that Laplace transform is applicable to linear time invariant system, which is we call LTI. This I is invariant system, okay? Invariant, okay? Invariance. Uh, so the time variable in the equations, if the time t in the equation is a continually defined variable at every time, from minus infinity to plus infinity, then the equation is called continuous time equation. And if this time variable t is defined only at discrete instants, so then the corresponding equation will be called the discrete time. Previously, what we have seen, they are all continuous time. And so what about the discrete counterpart of this equation? Can anybody tell me what will be the discrete counterpart of this equation? So we will do it in the next lecture. Thank you very much. And if you have any question, please write me here on m.sabi@dsu.edu.pk. Thank you very much.